Alright, hell yeah. So, in this video, we're going to go over the entire process of solving difficult differential equations. And so, this is a subject that I probably should have failed out of and then taken it again because just the whole, I didn't even know what was happening, you know. All right, hell yeah. And this is the hardest thing of like, what does the slope tell you? Well, I like to think there's two different ways to look at like math equations and physics equations. Like let's say I have a kinematic equation where you got a projectile going up and coming down. That stuff usually takes like about 4 to 6 seconds depending on where you're throwing it, and what you're doing with the projectile. So in this one, I don't know. I just like to say, hey, let's run it for a second. So I'm just going to use the tagline, let's run it for a second. Because in kinematics, we might be using time in seconds. And so that's going to be the unit of time. And then and that you're going to have graphs where that this independent variable, your horizontal axis, is going to be like time. That's your independent variable. And then you're going to have 1 second, 2 second. Cool. So for this simple example, we're going to have a table where x is one of the sides of the table. This is 2 meters. And then this equation gives us the area, and that's going to be 4 meters squared. So, and this is also, like, your differential equation teacher is not going to tell you this, because this is Algebra 1 and Algebra 2 stuff, where it's like, hey, is this a function? Like, first, is this a function? If I have a table and I make the table really tiny, okay, so let's say I can't even graph this side, so that side's just going to go away. Still a function. So that's one aspect. That's probably the second aspect of a function, is that you don't, if I just have an input of x, if I have my independent input, let's say x is negative 2 meters, that doesn't have to give me any solution. That might be a nonsense value. My independent variables, just because I chose one, it might be nonsense. And so I don't have any solution there. That's fine. It's still a linear line. And so what a linear equation cannot do is overlap itself. And this is kind of fascinating. I just did for tutor.com, I solved the Algebra 1 and the Algebra 2 test to be a tutor, and it was during that test that I'm just like, oh, the light bulb went on. Yeah, this is a very important aspect, or just definitionally, what is a function from a fundamental perspective? It's an input. You're doing an input number, and you're getting a number out, or you're getting no number because it's nonsensical. You know what I mean? So those are the only and let's say you're always getting an in and out. The most important thing is you're going to put one number in and you're going to get one number out. And your independent numbers are the most important. Because let's say I put in the number -1. Could I get the number 1 out? Hell yeah. Let's say I put in the negative infinity, positive infinity, and I get 1. You know what I mean? Maybe this is just the line at 1. So y is just equal to 1. So every time I throw in an x value, and this is kind of fascinating. I'm going to slow down just for a sec. We're going to get through this. I mean, I don't want to make a long video, but I do want to make a video. And so if this is my equation, y is equal to 1, I'm going to do this. I'm going to say y is equal to 1 to the x to the 0. So now I can still say this is y as a function of x. And that makes sense to me because I'm just like, I mean, now it does. I'm just actually on the fly thinking about this. Because the y part of an equation, where you have like a, and then I'm going to say as a y as a function of x, that's typically how we write it. So the other ways to write this are as if you have a function where you have x. And you could write this just in words. You could say, I have a function where my input is an independent variable. And I'm going to write this out because that's eye-opening even just to me right now. And especially because in mathematics, algebra, these letters can be anything. So it's almost, I think, so now I'm going to like maybe switch gears just a little bit in my studies to be like, what is, saying things in words is probably the most fundamental thing you can do. Because a function is a specific definition, and we just defined it. A function has an input values, so these are going to be input numbers, input values. That's going to be called a variable. The input value should be negative infinity to infinity, which would be all real numbers. And because it's only singular, you can only have one input number. It's just pick one of those numbers between there, or it's that range of numbers. And then that, if you do put that number into a function, the whole point of a function is to have an output. And mathematically, you know what I mean, I guess that might be sound, but also we use functions to explain the real world. So I get that. Yeah, hell yeah, we use functions to model maybe the area of a table. All right, hell yeah. And then just back to, you know what I mean, we have the ability to have any independent, the independent variable can be from negative infinity to infinity. Doesn't mean that all of these numbers are going to have an output that makes sense. They might be undefined for a range of numbers. And so sometimes you have functions that, you know, like the logarithmic function can't be, you can't put a negative numbers in the log function. So I think it goes like this. It might cross at, you know, log of 1, natural log of 1 is 0, and I think, and then it just kind of does that. I still think it goes to infinity, you know, in that direction, even though, yeah, because we're going to talk about that, because this probably goes to infinity. It just does so slower and slower and slower. Just like, you know what I mean, this probably as x, well, I mean, yeah, this also approaches infinity this way. If you flipped it, if you said the y was your independent variable, let's say the y is your independent variable, and you're just wondering if this x value will ever get to infinity. Yes, it will. And then it flipped this way, y is equal to x squared. Hell yeah, you can put infinity there, and that makes sense, and stuff like that. All right, hell yeah. Let me go back to this. This is very difficult for me to explain. I don't know why. It doesn't roll off the tongue. But if I do have a table that has side of 2, it has an area of 4. What does this equation say? This equation says if I change, I'm just gonna, I don't know if this is gonna sound right, but I'm gonna say, hey, this equation says that the change of this function, I'm not even gonna use those words. I'm just gonna say when my table is 2 meters, this number says 4. What does that mean? Well, just like I had the kinematics problem that I said I'm gonna run for 1 second. I'm going to run this for 1 unit of my independent variable. So my independent variable is meters, and 1 meter is 1 unit of it. And so I'm going to change my independent variable by 1 unit. So does that make sense? In kinematics, it can be like, hey, what happens if I run this for a second? You know what I mean? Maybe my inputs are like this. I'm not going to talk about that. But hell yeah, so this makes sense to me. I have a table that's 2 meters by 2 meters. This number says 4. What does that mean? It means that if I make a 3 meter by 3 meter table, what do I expect the area to be? I expect the area, if I increase it by 4, so this, 2 things. One, this is a number is 4, and it's positive. So that means that if I'm going this direction, if I increase the side of the table by 1 unit, the area should increase by 4 meters squared. And so let's try it out. This has an area of 4. This has an area of 9. And we increased by 5 meters. Now, I like this because you're not getting exact answers. But this is where, that's what this number means. It says if this should be the change at this point, this will be the change, in the area. But then as you go to like 2.5, like right there, well, what are you gonna hit? You're gonna hit what's the slope on this? This is 2x. So if you went to 2, 4, if you went to 3, you'd be at 6. And so if you went to 2.5, your table would be, yeah, so if you had a side of 2.5 meters to 2.5 meters, and you still increased by 1 meter to a table of 3.5 meters to 3.5 meters, it should increase by an area of 5.5. And so let's pull out the calculator. So we have 2.5 squared, 3.5 squared, this minus 6.25. Bummer. That minus 6.25, and that's 6. And so, yeah, and so the error there was just 0.5 error, where the error here was 1. So, all right, let me say that in another way. Let's say I was making something like just a 2 meter long, you know, something, okay? And then it had, oh man. Yeah, so length. Let's say length is 2 meters. And then the derivative is saying, hey, let's say this length might be changing. You know what I mean? And so, oh, that's a bad example. All right, we're not getting the right answer because this change is continuous change. This line is not like this. We're not just like getting a constant change. It's not like if I make a 2 meter table, then this is 4. And then if I make a 3 meter by 3 meter table, my area, yeah, so I mean if you wanted to do that, I mean you would have a table that had this, and then if you went up to 3 meters, you would have a table that's just 4 more. So this would be a 3 meter table, and if we made it square, you would have 1, 2, 3, 4, 5, 6, 7, 8. I mean, you would essentially have all of these except 1. You know what I mean? So you can't make a square table if you have a constant change. So if you're constantly a constant change. And then if this was a 3 meter table by 3 meter table, and it wouldn't be that way anyway, you'd be missing a piece. But then if you went to a 4 meter by 4 meter table, you can still only increase, like this has to increase that way to 4, this has to increase that way to 4, but you only get 4 more pieces. So I'm going to fill in that piece, and then 2, 3, and I can only fill in 1 more. So I'm not making square tables. I think that is a good way. So if I'm saying this is still a 3 meter by 3 meter table, because there's the length, but it has pieces missing. If I go to that 4 by 4 table, I get it. If this line is constant, sure, I get to increase the area by 4. So let's do 1, 2, and then just 3, 4. So there you go. There's a 4 meter by 4 meter table. You know, those two lengths are 4 meters. I think this is actually turning out to be a good description. It's still hugely missing pieces, but it's still a 4 by 4. And this actually works because if I increase, if I did a 5 by 5, I get to still put 4 blocks in. So I can always fill those 2 blocks in, and then fill in 2 more. You know what I mean? And so I can always make the table of that size. So that's a pretty decent example. All right, but because this is continuously changing, I mean, I'm going to make a 2 meter by 2 meter table, and I can't just do like a full jump. Doing a full jump from a 2 by 2 meter table to a 3 by 3 meter table is not represented by this, because that's a whole jump, but it's close enough, and so that is enough said. We need to get on with this. Hell yeah! Alright, let's try to burn through some of this stuff. So this is a differential equation, dy dx. It's going to be constant, so it's a constant change. There is a function. And a function has a derivative. You know, even if you have portions of a function and then maybe like this, each of those portions of the function, you know, that's continuous, that piece has a derivative. Sweet. And so that's good to know. So there is a function because there is a derivative. So if you have a derivative, and that's the definite, I think this is like a fundamental principle of calculus. If you're saying that this derivative is this line 1 that goes to negative infinity to positive infinity, you just have some information. You know that there is a function that also goes from negative infinity to positive infinity. If this derivative is continuous on an interval, then the function is continuous on an interval. So that is a piece of information. I don't know anything more, but I'm just going to end it there. So hell yeah. So where the derivative... Alright, so this is a derivative where the derivative always equals 1 for all values of x. Okay, so let's see what I say. I like to think, yeah, and so just right here, this is still a function of x if I say dy dx is 1 to the x to the 0. I don't know if you can formally do this, but it's like, hell yeah, that's a function of x. And x to the 0 is always 1. So I can throw in any value of that independent variable. Because we're talking about graphing. So here's my dy dx. And then, so here's my independent variable x. And it's 1. And so it says I'm going to input any value of my independent variable, and the output is going to be 1. So where do you input this independent variable? That's why I like to do x to the 0, because I can see it. You might not be able to do this when you actually use the tricks of the trade of integration and differentiation, but for the most part I think you could. You might run into some issues there. Alright, hell yeah. So that was page 1. Holy hell. It's going to be a 3-hour video. Alright, let's try to bust though. Okay, so we have this function y is equal to x. That's y is equal to x. Okay, so can I rewrite this? Because a lot of these differential equations are just like, okay, I see a y there and a y there. This is y squared and this is y, but I've never seen that before. I don't even know what that means. And so let's take a very simple example that we know, y is equal to x, and just add more y's. I'm going to, what do? I'm going to add a y to both sides. I think that's what I did. I'm going to add a y to that side and add a y to that side. Hell yeah. So now we have y plus x on that side and then 2y over here. Okay, hell yeah. And then I'm going to take this and just subtract a y. And then I get the original equation. So this equation, I've never seen it before. It looks funky, but it still just represents this. If x is my independent variable, and you know what I mean? If I throw in a 0 here, and that's what I do, let's see. So, oh yeah, let's get the y on that side. So that's all I do. I just subtract a y to get y on this side. So now we have y. No, what the hell do I do? You know, why did I rearrange this? So this is the equation I'm looking at. I'm going to get y by itself. So I'm going to get x to the other side. So yes, so we have 2y minus x. So y is equal to 2y minus x. So this is the equation that I'm going to kind of play around with. Y is a function of twice itself minus x. Cool, so that's the one that I wanted to use. And then if x is 0, this equation still has to be satisfied. And then the only way this is satisfied is if y is 0. If x is 1, I'm going to put a 1 there, 1 here. And then I'm going to subtract 2y from this side. So then I have negative y over there and negative 1 right here. Y has to be 1. And even through this process, if we're keeping tabs, this equation is this. You know, those two are the same. So if I had an x of 0, y should be 0. If I had an x of 1, y should be 1. And that's what we see. Okay, hell yeah. So then I wanted to come up with my own problem where I'm just like, well, let's not I mean, if the derivative, if I'm saying there is a derivative, dy dx, that is equal to 1, the number 1, I can just raise this x to that derivative. You know what I mean? Because, or let's slow it down. If I say this is a function, all right, hell yeah. So now I don't know how to define terms. I don't know if this is a function. I don't know if you classified this as a function. I don't know if this is a function. I don't think it is. I think it's probably called something like an expression. I have no idea. But is this a function? If I throw in, I don't know, like what's the definition? Well, wouldn't you have to choose an independent variable? And then you have a lot of things going on here. Like, couldn't I... Yeah, so I don't think this is actually a function until you actually get something explicitly on this side, whether it's y prime on this side, whether it's x on this side, or whether it's y on this side, and then the other variables on the other side. And even then, when you're just graphing, so if I do have this dependent variable, either, one of those three, and then an independent variable, I can only have one independent variable, right? Because I can only have one input from my independent variable, and then one output. Even if you have equations that are, if you have equations that you can change, you can throw in an x. So if I'm going to solve this for y prime, I can put x is, I have two, is that called two independent variables? I'd have to look that up. But until you put a value in for something, let's say I put in a value for y, then it looks like, now your x is your independent variable that you're looking at. So you have to choose a value, and then you can, have your independent variable be the last value. Don't quote me on that, though. Holy hell. All right, hell yeah. So I don't know if I'm just knowing that this is a function, you know what I mean? Like, and I haven't changed anything. And so by putting this derivative, or a y prime right here, I can write this as y is equal to 2y minus x to the y prime. I still haven't changed anything. All right, hell yeah. So we're back. Okay, I think we need to burn through here. So yeah, this doesn't change anything if the derivative is 1. And so, then, you know what I mean? Then it just goes to this equation, and let's see. I don't know, but yeah, but you don't know. So, but if this is, you don't know by inspection that this dy dx. So yes, if you do have some sort of funky equation, this kind of gets into analyzing this equation. From a numerical methods perspective, this is really easy to analyze, and I don't know why this isn't taught, almost 100%. Everyone's just kind of into like, hey, let's learn how to solve differential equations, and let's figure out how to integrate different various, that's why they have integration bees and stuff like that. But just from the fundamental, if you have numerical methods, you're just like, well, we're just in. And even my brother, with lasers and stuff that he's doing with a quantum physics background, he is using numerical methods to solve differential equations. You know what I mean? So that's what you're going to be doing anyway. Why not learn it? Okay, so yeah, I don't know by inspection this dy dx is equal to 1. I can just choose something. Maybe that's what I did. It's like, let's say it just is equal to 1. Yeah, so it's kind of like back and forth. If I just choose 1 here, does that work? Yes. So this is a 1 right there. I'm going to get the 2y to the other side. This becomes negative y, negative x. Get rid of the negative. Y, the function now is y is equal to x. The derivative of that function is 1, and so we chose correctly. All right, hell yeah. So let's see what we do. So if I do have this equation, and then, yeah, so we're going to explore. I don't know what this is. So I'm just going to throw in a value. I'm going to say x is 0. You know what I mean? Because I'm just going to kind of choose that as my independent variable. I'm going to say, hey, you know what I mean? I'm going to graph this. I'm going to throw in a value of 0. And we got basically two graphs going on that hopefully mimic each other. So yeah, that's the nuts and bolts. Look at this. I just did two graphs where this. So I have a funky equation. I'm going to say my independent variable is x, and this is going to give me a function, like whatever it is. It's going to be that function. And then I'm going to plot this, and then I'm going to find the derivative, and it's going to be that. So let's go through this process. If x is 0, cool. 0 to any number. 0 to any number is, 0 to any number is, hey, let's forget about that. But the 0's downstairs. Is that? Yeah, 0 to a 1. Yeah, anyway. 0 to any number is 1. Hopefully I'm saying that right. But yeah, if x is 0, that term goes away, and this y term has to be 0. Alright, so we got our first point. First point's right there. We found 1 point. And so this method is going to be inaccurate, but it's going to be close enough, because now we're just going to get another point. And then once we have 2 points, let's say I get this other point that is going to be 1, 1, and then we have 0, 0. Now I have 2 points. I can find the slope between those 2 points. Now this equation might be doing something like that, where this isn't the actual slope. You know what I mean? And if this equation was x squared, the slope right here at 0, 0 is going to be 0, and the slope right here at 1, 1 is going to be 2. It's going to have an average slope of 1, but that's what we're finding. But that's where we can throw in a third point. If we throw in a third point at like x is equal to 2, and we still have a slope of 1, well, we're just like, oh, okay, now it's kind of looking linear. Does that make sense? And I don't go into it for this video, but I solve a lot of physics problems from a numerical method perspective of just finding 3 points. Once you have 1 point, find 1 point that way, find 1 point the other way, and then you have 3 points, which then you can find your y double prime. You know what I mean? Your second derivatives. Okay, so we need one other point. I'm going to choose if x is 1. So now we have this 1 to this slope, but this is, or 1 to the derivative, dy dx. But we have 1 to any number. 1 to any number is always 1. So cool. So that part is going to be 1. So let's do this. So we have y is equal to 2x minus 1. I'm going to get these two y's to the other side. Now we have negative y is equal to negative 1. Get rid of the negative. And on both sides we have y is equal to 1. And that's our second point. It's obvious. But now that we have 2 points, I'm going to use the definition of the slope of a line. Or just, this is change in y, change in x. Even though we want an equation, we want dy dx, where we input the independent variable. So I'm going to input x is equal to 0, and I want to output that value. I'm going to input x is equal to 1, and I'm going to output that value, and it might be different. And if I got 2 different values, this process is going to give me the average between those 2 values. Alright, so the change in y value, so this is x, y, x, y. x1, x1, y2, y2. So the change in the y values is going to be 1 minus 0. The change in the x value is 1 minus 0. So we have the slope of 1. So that's what we find from that first point. And then we're going to check to see, because I just said this was going to be an average value, it might not be correct. This is what we found. We did not find that. But let's sub this into this dy dx and see if our equation still holds for both points. If it holds for both points, then I think we're, correcto mundo. Don't quote me on that. But now we have this equation with the y1, x1. That's 0, 0. So 0's all around, and we have 0 is equal to 0. The second one was 0.11, so this is 1, this is 1, 1. So we have 1 is equal to 2, and this is 1 to the 1, because that was the slope at that, both this was 1. but this was 0 to the 1, and this is 1 to the 1. And so we have 2 minus 1, and we have 1 is equal to 1. So both those equations are 100% accurate. Cool. Now, for this one, if we do that process, you wouldn't get 100% accuracy. You're going to get an approximation. So that's kind of the next place we're probably going to explore. All right, hell yeah. I feel like my videos are good because I'm the only one that's going to explore with, like, limited knowledge. I was just like, well, I graduate. I got enough knowledge. You know what I mean? But it's still, like, you know, yeah. Like, this stuff's hard anyway, and we're not even doing what the teacher is actually. The teacher just goes, I don't know. I can just imagine the teacher is going to be like, yeah, this is complex, and these are the steps to actually solve a differential equation. That's going to be at the end of the video, and it's just going to go through these steps, and yeah, it's not obvious, but so we're in the process of doing it our way, numerical methods. Oh, so we pick a third point. If x is 2 on this equation, and I'm going to guess that the slope is 1, so that's all I did. And, well, I don't know why I would guess the slope is 1, but, you know, I should be just, let's see. All right, whatever. So, is that what I did previously? I don't even know. To get these values. All right, let's just see what I did. So, x is 2 to the 1, and then I'm going to solve for y. So it's going to be -2, negative y is 2, and then I have my third point. And then I'm going to oh, and then so I'm just so if I chose that slope, I'm going to get an x and a y value. And then if I got an x and a y value for this, I got the x2, y2. So then I'm going to compare and then figure out the average change, you know, change in x, change in y. And I didn't even write that right. It should be change in y, change in x. That should be flipped. Sorry about that. But that equals 1. All right. That page seemed like it sucked. But cool. Now we got into the juice. So this is our equation. We have y is equal to y multiplied by the derivative dy dx plus x is equal to the square root x squared plus y squared. And then so let's just play around. Same thing. If x is 0, cool. That goes away. That goes away. Now I have y dy dx is equal to y. I mean, you could do this. You can play around with the equations. And then the y's are going to cancel, or just y divided by y is 1 on this side. Let's get the y's over there. So we have y divided by y on this side. So dy dx is equal to 1. So even with, and it's kind of fascinating because we graph this in Excel. Oh, yeah, let me pull up the Excel graph. Alright, hell yeah. So I'm back with the Excel spreadsheet. And this is just from the numerical methods perspective. We graphed x, and when x is 0, that's 0 right here. It just puts it as something to the negative, huge number. But anyway, the derivative is 1. And so there you go. And hell yeah. So we just put in when x is 0, the derivative is 1. So now we know that. And now what can we do? I imagine we could. I don't know if I try to solve for y. I don't think so. Oh, and y can be anything. That was the deal on this one. Y can be anything because this isn't a or what up? Let's see. I'm gonna take a little pause. No, this works. That's cool. So there you go. In this equation, or whatever this expression is called, differential equation maybe. Yes, I mean we put in x is 0, and then we broke it down to where y can be any number. You know, this expression when x is 0 no longer has y in it. It just boils down to this expression. So y can be any number. I just said y was 0. And so, cool. and then at x is equal to 1. So I throw in x is equal, oh, and then what do we have? So we have a slope of 1, and so I just chose x is equal to 0, y is equal to 0. So if I'm trying to find this x-y relationship, when x is 0, y is 0, but now and this is that equation, and now I know the slope, dy dx, at least for one value. And so when x is 0, the slope is 1. And so that's the value. I don't know what the next value is going to be, but then I know that here the slope is going to be 1. And so let's just run this for 1, in both directions. So if I go this way to x is equal to 1, now I know my next point is going to be x is equal to 1, y is equal to 1. And so that's what I have right there. It's kind of like running it for, and then I'm just going to choose those two values. And then I'm going to choose those two values and then solve for what my next slope is. So that's what I did there. You know what I mean? You kind of have three variables. And so hopefully that's what I did. I'm sure there's different ways to play around with it. But I'm going to say x is 1, y is 1. So this becomes square root 2. This is going to be 1 right there, and this is going to be 1. So I'm going to get this 1 to the other side, so I have the square root 2 minus 1. So I have 0.4. So just is the derivative. So now, at the value of x, so this is x, at x is equal to 1, the derivative is 0.4. So it's going to be right there. And then at x equals 1, the slope is now not 1, but it's 0.4. So that's kind of the direction that I'd be going. And since I'm continuing this direction, this is the trajectory. So then at x is equal to 2, I'm just going to say there's the point. And so that point is going to be x is equal to 2, y is equal to 1.4. So that's what I have right there. Then throw those in and then see what we get. And so in that process, I get square root 6 minus 2 divided by square root 2, and I get 0.3. So then this slope right there is 0.3, and then so the next value is going to be just a little bit less. And then so we have this trend going on that looks something like a square root. So our y equation is like the square root of something. So I can see that right away. That's kind of the trend of that equation. And hell yeah, and that makes sense. I see a square root there. You know what I mean? Okay, so let's see if we can do some more burning. At this point, when I said x was 0, I could choose y to be any value. So now let's go back to our, you know what I mean? This is the initial condition for this differential equation, and this helps us solve for a specific function. And this is when x is 5, y is the square root 56 was about 7. You know what I mean? 49 is 7, and then 8 is 64 or something like that. So this is going to be 7 point, I don't know, who cares, 7.5. Alright, so let's see where we take this next. So I have, yeah, so this is what we had. We had when x was 0, this was the slope. But x can equal any number. And so that's where, if I don't specify an initial condition, this can represent a whole slew of graphs. And so at x is equal to 0, the y can be 0. And I don't even know if I even said this right. Oh, I probably messed this up. Yes, yeah, because this equation was y divided by y. So I come up with something totally different here, and maybe I just made a mistake. But let's say your slope was a function of y. So let's say when you boiled this expression down, you know what I mean, you got dy dx is a function of y, and so I'm going to choose an x value of 0. Yeah. I'm going to choose an x value of 0. My y value is 0. So that's 0, 0. So that value is 0. So that means my slope is 0. If I chose a x value of 0 but a y value of 1, this indicates that my slope is 1. So I showed a slope of 1 at y is equal to 0, 2. At that coordinate 0, 2, where y is 2, my slope is 2. At 4, my slope is 4. Down here, it's going to be negative. Negative 2, negative 1, negative 4. But yeah, I probably made a hiccup thinking that this was the problem that we're solving. Alright, but let's walk through here because I do set up the steps to do this in Excel. So I'm going to choose x is equal to 0. If the slope is 1, I said then y is 1. I think I would do that in the other way. If I don't know. Or if y, yeah, so if x is equal to 0 and y is 1, this slope becomes 1. But yeah, the huge hiccup was I was thinking this was the original problem. It's not. So if y can be any value, then the slope can be any value. You know, just for this new problem that we're looking at. So if my y value is 0 and x is 0, y is 0, the slope is 0. So in this process, steps, so you need to choose a value of y. Oh yeah, so this is fascinating because to solve this differential equation, I'm just like, hey, let's start with x is equal to 0. That gets rid of a ton of stuff. And this differential equation still has to jive. It still has to, and then the y's basically cancel, and then so you have this derivative is equal to 1. And so, and that's, so I should be looking at that. So this is the problem that we're doing, so let's see if I can do the steps. So I just lucked out that, hey, when I chose x is equal to 0, it really simplified it, and I got my first value. I can have y be anything. The slope's not going to change, so that part was for this kind of hiccup. Okay, so start with x is equal to 0. Choose your y that you want, and let's see. Oh, and yeah, let's see. Like, what is the equation that we actually have? Alright, hell yeah. So, you know, this is the initial condition. So when I throw in a value of 5 here, and a value of 5 right here, my y value is square root 56. I'm going to throw those in. And then I need to find, this is the only variable left, and I need to find the slope that makes the equation equal on both sides. So that's it. You know what I mean? And then so that's where I started my Excel spreadsheet. So I would start I'm going to start at, you know, y is equal to 5, or x is equal to 5, 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5, 6, 7. That's kind of where this point is, about 7. And the slope on that, you know, let me pull out my Excel spreadsheet. So at y is equal, oh, this doesn't have it, so maybe I'll print out the full Excel spreadsheet. Alright, hell yeah. So we're back, and what we're doing is this initial condition says our x value is 5, and our y value is you know, about 7, square root 56. And so we're going to come to our graph where this is our x values, and this is our y values, this is our x values, and this is dy dx. And so, so this is our graph, x, y, x, dy, dx, and we're going to go to 5. And it says our y value is 7.48, which is the square root of 56. And our solving for dy dx, that's going to be, sorry, dy dx, that's going to be 0.5. So cool. So our slope right here is just going to be a half. It's not going to be 1, it's going to be a half. And then so then I can find the next point. And the next point at, you know, at 6 should be 7.7, about 8. And it is. There you go. So it's about 8. So hell yeah. You know what I mean? And this is accurate. Yeah, so yeah, saying that it would, using this as the slope to make a 1 full jump is going to be the more inaccurate way. We're going to do this in 1/10. Our change in x is 1/10, and in that step we can have a new value. And yeah, so the first thing is just solving this equation for dy dx. And cool, so let's see what we do. So we're ready to go to the next page. Hell yeah. So let's find, and the whole idea is finding an equation, y of x, aka solving the differential equation. So this is the differential equation that we have. I can at least solve for y prime. And yeah, for these equations, you're just like, hey, is anything just by itself? Because if you have an equation with something by itself, it's usually easy to isolate it to one side and get everything else to the other side. And so that's what we can do. We can subtract an x, and then we can divide by y, and then we can have this. And so, and now when I throw in the initial condition of x is equal to 5, 5, 5, and then y is equal to square root 56, right there and there, I get this value. And that's going to be 4 divided by the square root of 56, which is that 0.53 that we looked up from the Excel spreadsheet. I just did a bunch of things to reduce this. But anyway, in Excel, so at 0.5 in Excel, my y value is going to be this. I'm going to change that value by 0.1. I showed you that we can just change the value by 1. My next value is x is equal to 6, and what's my y value? Just from an intuitive perspective, the slope is going to be positive 0.5. So my next y value is going to go from 7.5 to 8. 7.5 plus that 0.5 in change in slope over that unit. But in Excel, if my change is just going to be 0.1, we're going to kind of talk our way through this. And my slope is still going to be that dy dx value. So to find the new y, when x just increases by 1/10, what do we do? So my x new, so new x is just the old x, which was, let's say, 5, plus the change in x. So that was pretty easy. My new x is just 5 plus 0.1. My new x is 5.1. And so, but what's my new y? The change in y is going to go from 7.5, but now it's going to be increasing. And we can look at our Excel spreadsheet just to make sure we have something to target. From 5, it's going to be 7.48, and then it's going to go to 7.53. And so the difference there is just going to be a difference of, well, 1/10 of this. Is that right? 7.48 plus 0.053 is 7. So it's 1/10 of that, because I'm only going 1/10 in the x direction. My change in y, so because slope is usually change in y over 1 unit of x. Run it for 1 unit of x. Run it for 1 second. So that's kind of how I think about the independent variable. And then things, because rates of change have units that involve, the units on this are going to be some sort of change in something that has units, divided by a change in the units of the independent variable. So it's the change in the units of that x variable. And so, and that's, because if you get a value for that's what the units are going to be. And so if I just change my x variable by a full unit, that y value changes by a full unit. If I change my x value just by 1/10 of a unit, that y value just changes by that much, by 1/10 of that much. Cool. So the equation, so the change in y is going to be that 1/10 times that slope, times the rate of change, dy dx. The differential, the value of the differential, this is the value of the differential equation at the input, at the chosen input, at the x chosen input. The input is x equals to 5, and that is the value that we're getting. Cool. So when we have this new x and y value, now we can, what are we going to solve? These two, yeah, let me read through this. All right, hell yeah, I was just mentioning that, you know, these two technically kind of cancel out. If this change was incrementally small, then yeah, it looks like kind of those cancel, and you just, but that's all I mentioned there. Cool, and then you're just going to start the process over again. Now we have a new x value, we have a new y value. We can plug those into this equation and then solve for our new slope. And that's what we do. And we just do that process on repeat. That's all I did in Excel. I said, here's my initial x, here's my initial y. I'm going to solve for the derivative, the slope, the dy dx, the y prime. And then I'm going to use that slope to get to the next value. So this is how I got this new value. I'm just going to increment the x value by 1/10, and then this is my new y value. And then I get to solve for a new slope. That slope slightly changes, and then I'm going to extrapolate the next value. So I'm always, in this process, you're always going to have error, and you might accumulate error. I think that's a correct statement. But hell yeah, it works great, and we're very accurate even just at 1/10. Having x change by 1/10. All right, so let's see what the next part of the process is going to be, and we're almost, I don't know, but anyway. So I want to say that we're just so used to using equations in the form of y is equal to something something x. This is my term for saying something something x. In this case, y is equal to x squared. And then we can make that equation look like this. And then it's easy to use the rules and get a differential equation, dy dx, or y prime is equal to 2x. I don't think I bat an eyelash of just looking at it like this. But I don't think I've ever charted this, on a sheet of paper where I put dy dx right here, or a y prime, and then have my x still just be my independent variable. I never think of it like that, and so this is a good time to think of it like that. Okay, hell yeah. And so we definitely went over that at the very beginning. Alright, so now we're going to read our Excel graphs, because this is what we did. I started at x is equal to 5, and I went to -10, and I went to 10. I don't know. I was just like, well, I started at 5, might as well go to a negative number, and then 10. So I just chose -10 and 10. But I think from x is equal to 5 this way is kind of the sweet spot. A lot of funky things go on. So then if this first equation is used, to model something, so if you came up with an equation to model something, maybe your x value is time. And I don't know, and your model only works at year 5 on. You know what I mean? Like you're setting up some sort of growth thing and, population thing. I don't know. I mean, that's kind of what differential equations are used for. But always be thinking about that. And even in physics, if you have an equation, not what is the range and domain of this? Like, could you put in negative infinity, positive infinity? Is there any numbers that are nonsensical? That's a good check from a mathematical perspective, but then just from an intuitive perspective, it's just like, when is this equation actually modeling something? Maybe it's only when x is positive. Maybe it's only when x is 5 and greater. You know what I mean? And so, because if this equation only works from here to there, yeah, then we don't have any of the weirdness that we get with the negative numbers, just because we have, squares and square roots. And because so you can see that so we have a slope that's kind of steep, shallower, less. And so that's what we have. We have this graph as our slope. This was -10 to 10. That didn't come out right. So, well, I don't know. So here's the same graph from, maybe not. I'm trying to think. So I think these two graphs are where I just plotted from this point on. So this is nonsensical to the problem, but yeah, this is the curve that we were looking at, and this is the differential curve. And hell yeah. And it seems, yeah, it seems like it works from negative, you know, close to -3 or something. Maybe just -2. I think this was -1.9. Cool. All right, so we're going to use that. All right, so there we did it. You know what I mean? We graphed our equation. We kind of even honed down that this might be the more reasonable place to look at this equation. It looks like the square root, you know, a square root equation. You know, y is equal to the square root of something. So the y equation looks like y is equal to the square root equation. This looks like it's going to 0. And I already know the solution, but so if this is dy dx, how do you get something going to 0? Make a fraction and then put this value and make it get real big. How do we do that? Put your input value as x, and then that's going to get real big, and have your output value. I don't know. You know what I mean? Just have your output value. If this is y, and this is kind of going like this, you know, it's not getting as big. The slope is almost going to 0. That's what we're having here, because as x gets huge, then this, so yeah, you just need this not to blow up as well. So you want an infinity downstairs, and then just a normal number upstairs, and then that will go to 0. So if that's, and so how do we do that? I don't know, but we can take a look at how that's done from the final solution. Alright, so now I'm just going to walk through how you would actually solve for this. But we just showed the Excel spreadsheet graph, and we got our solution. Whatever the equation of this line is, dy dx, no, this one. Whatever the equation of this is, then we can easily find the derivative. So if I knew the equation of this, I could find the derivative, or I could just use Excel to plot the points. And then so I can use these two graphs and the numbers associated with them to solve a lot of different problems, because I know the value, any input of x input has a y value, and that same x input has a slope. So I can find the derivative at that point. Alright, hell yeah. So let's see how they solved it. And this is how probably my nephew is solving these in his class. And this is new to me just because unless you're a math person, even in engineering, you don't have to do this much. I mean, it's a good skill. But I should have failed out of this class because I don't know. I even went to the teacher. I was like, I have no idea what you're even talking about. Like, it's so foreign. And it's and I get why it's foreign. I get why it's foreign because no one's teaching this from numerical methods. No one's just after doing like the Excel charts, it's just like, cool. I know that I can take any. And that's okay, so this is my take home point. Is especially with integration and these differential equations especially. If you use numerical methods, you'll always get a solution. It might have error. Those errors might accumulate and be horrendous, but you can always use numerical methods to get a solution to the differential equation, to get a y equals x equation from a plotted perspective, and then you can find the dy dx from that. Alright, hell yeah. Yeah, so numerical methods, you can find solutions to the hardest differential equations out there. It seems like there's no limit of how complex something could be as long as you're choosing values. And if something has an initial condition, then all the variables have to be, even if this was x, y, z, multiple variables, if you have an initial condition, it has to say what all those variables are. You know what I mean? And then so the only thing left is your differential equations. And I'm just thinking on the fly, you could have y double prime, you could have y triple prime, and so yeah. So that's not going to work. Oh, that's interesting. So yeah, but for these, I don't know. I mean, it's like I don't know how hard differential equations can be that have solutions, even from a numerical methods. Maybe that seems like I would run into some hiccups. But all right. So even this method worked from a numerical perspective because I could get y prime by itself very easily, and then set that process up. All right, let's go over the solution. So here's our differential equation, y dy dx plus x is equal to this. So we're just going to rearrange for dy dx. Get x to the other side, divide everything by y. Now I have dy dx isolated. I think before I switch to another page, like, what are we trying to do? We are trying to get rid of a variable. So I want to get rid of the independent variable. And that's just from, I don't think that's super obvious. It doesn't say this in Google solution. But what you're trying to do is not have an x input. Or where, like right here, I have y's and x's. Y's and x's. Oh, yeah. Well, I don't know. So maybe we should just flip the page. But it's just good to do this to be like, well, what do they do? Well, they're going to take these x's and make it x divided by y. I'm sorry. They're going to take these x's and go x divided by x. Let me say this again. So they're going to take like this x and they're going to go x divided by x multiplied by x. So I guess they're going to take that x and then multiply it by a 1. And so what this is going to do is, they're just going to divide. They're going to multiply everything by x. So let's talk about this, because if you took this by x, and then and they're dividing. Oh, bummer, dude. All right, holy hell. You know what I mean? So this process is just to get, what you're trying to do is get this. You're getting this equation in terms of a variable y over x. And if you do that, then you can do a substitution with another variable v. And then so what it looks like is just, I mean, at least this side for now looks like 1 plus v squared minus 1 divided by v. When we do this, we'll talk about this side of the equation, because we're skipping ahead. This side is v plus x dv dx. But from here, what you're trying to do is, like, this only requires separation of variables. Because now, sure, you have a lot of these v's everywhere, but the x and the dx are super close together, and now we only have one x variable. So those two can be on one side of the equation. This dv can be on the other side with this. So I can subtract this v over here, and then, the dv's got to be on this side. The dx comes up here, the x goes downstairs, and then, this looks like a natural log once you integrate. This would go to the other side, so we would have a minus all this, and then you'd have that dv over there. Is that how you do it? Probably not. I would subtract the v over here to get all of this on this side, and then take this whole thing and bring it to the other side. 1 divided by that whole thing, then you have the dv right there. Holy hell. So this process, I don't know how you would intuit this, but there must be similar problems where you're just like, oh hell yeah, when I get y divided by x, and it doesn't change anything. What this essentially does is get an x right there, there, and there. It gets an x in all the different terms, and then so what can you do? Or how did they even get from there to there? Alright, I'm going to do this. This is bothering me because it looks like Google has an error, because there's no way you can just do this, have an X on this side, and then just get rid of an X on this side without getting an X on that side. So what's happening here is there's got to be an X on the other side, right? We'll see. So if I have this equation, and I'm going to what am I going to do? Alright, holy hell, that sucked. Okay, so they're taking these, they're gonna, well yeah, so yeah, it's like two steps in one. In the process, you can first just change this y to y divided by x. But then in that process, we have to make this equation, and then so that's going to be right there in the bottom. If I do y divided by x, let's see. The equation still has to look like this though. So right here, that's going to be y squared divided by x squared. This, if I'm going to add those two together, this is just x squared. I have to multiply top and bottom by an x squared. Cool, now I can add those. I didn't change anything there. And so now this is going to be alright, this is the part of the video where I'm going to take a chill pill, slow down, because if I had to solve one of these differential equations, I would get to here and then be like, what's the next step? And because I have two variables, x and y, and they're separated by addition. So that's the kicker. I can't get these variables together. So in this process, what they do is get the variables x and y together as a product. Now you just have x divided by y. Now I have a product of x and y, and so that seems to be money. I don't have x plus y somewhere. So let's say I do, and I think you could probably do this in a different way, but no, I mean x is your independent variable. So I want to get rid of this x value. How would I get rid of this x value right there? I would divide it by x. So that value I would just divide by x. Alright, so let's do that. So this negative x, I'm going to just divide by x. This x squared, I also have to divide by x. And so let's do that. So I'm just going to take the square root of x squared plus y squared, divide by x. I know that this is, if I want to get this under the square root, I can do this. I can say this is x squared square root. That is still dividing this by x. Now, since these are both under the square root, I can get, it's the same thing as this, x squared plus y squared divided by x squared. So that's what I have. And then since this is the denominator for both of them, then I can switch it up and be like, hey, this is 1 plus y squared x squared. And then I can see this is 1 plus y divided by x squared. So we're chill there. This was a 1. Alright, hell yeah, and now I know why I'm confused. I just took these two values and divided by x, and that's in the numerator. And I divided by x. I also have to take the denominator and divide by x. It's bizarre because all we're doing is taking this equation and multiplying by x divided by x. I'm just taking this x below and incorporating it into the upper part, the numerator, and I'm going to take this x and incorporate it into the denominator. And that's bizarring me. The fact that this x incorporated into this denominator is y divided by x. Like, that's so weird. But I'm used to that. Like, hey, This is your denominator, like your first term in your denominator that stays downstairs. If you have that term divided by another term, that gets kicked upstairs. So that is that term. And so that's why we did the divide by x upstairs, divide by x downstairs, and that is just like multiplying this side by 1. And so now we have our y divided by x there. This value becomes 1, and then this value becomes that. And so, we can move on. But yeah, that's brutal. But I think the take-home point was now our x and y are a product, and so that's useful. And maybe they don't have to be a product, but for this substitution, we have y divided by x. Cool. And then so substitutions, I'm fairly decent at them, is that this is an equation. So write v is equal to y divided by x, and then, and so, but what's this? dy dx. Yeah, I'm bad at this, but anyway, I'll just kind of walk through, kind of the process to the best of my ability. We can rearrange, they're rearranging this for y, so y is equal to vx. And then I can take the derivative. I can take dy dx. And that's going to be this term. So dy dx of vx is, well, dy dx of this. Well, and write it like this. D of this term, dx. You know what I mean? Maybe that's helpful. But this variable, if I was taking dy dx and it was just the x, we know how to do that. It's just 1. But if I have another variable that does change, and it's just not a constant, I can't just take dy dx of 2x as, I'm sorry, if y is 2x, I can't take dy dx Alright, holy Toledo. I was just saying that when you take the derivative of this, you can factor out the constant. So this is just dy dx of, and then, how do you do that? This is, and then your y value is, yeah, so if you're taking, this is just kind of the derivative notation. The derivative of a function, parentheses, of that function with respect to the independent variable. So as 2x changes, as you change this value by 1, how much does this change? Well, by 2. You know what I mean? So that's really self-explanatory. But if we're taking this, dx of vx, as this x variable goes from here to there, the x variable is right there, so it also goes from 0 to 1, 1 to 2, so just a value of 1. So that's how much that changes. When this x changes by 1 downstairs, 0 to 1, that x changes 0 to 1. Cool. But we don't know about this term, and so we write this as the product rule. And so, what do we have? So we have d dx of vx. And so this is going to be, and it was like this, dy dx of vx. So the product rule is, well, v changes and x changes. So we can write this, dy dv dv dx. And so that's how we write it, because these kind of could theoretically cancel out, and then you're left with that. So what is this? So this is And our y function is vx. So there you go. Our y function is that. So this first term is the derivative with respect to v. And am I even doing this right? Alright, let's try it. But so yeah, so when v changes, how does y change? Well, if that's assuming doesn't that assume that x is a constant? Oh, I think I'm messing this up. And I don't think this applies. So let's take a pause. Alright, hell yeah. So yeah, they're using the product rule. So if I'm differentiating this, both can change. So it's the first times the derivative of the second. And it's going to be with respect to x. So it's dy dx. So it's going to be the first, v, with the derivative of the second. So that's dx dx, that's 1. So visibly that's 1. Plus the second, x, times the derivative, dv dx of the first, which is just dv dx. That's the derivative with respect to x. So that's what we have. So this is dy dx. So right here in this location we have v plus x dv dx. And that's what we're trying to do, because this value right here is v. So now we have v. And then this is v plus x dx and then dv. And so that's the whole process, is to get this. So yeah, this value was right there. And then we just solve for that. The v's go in there. And then we can do separation of variables. Even though we have a lot of v's, we can get all those to one side. And then divide. And your dv and your dx have to be up top in the numerator. But you can have anything below them, just because that's going to indicate kind of natural log. The integration of that's going to be natural log. Alright, so hell yeah, let's move on. So there you go. So we're going to do the separation of variables. Let's get the dx upstairs right there. Let's get the x downstairs right there. So that part's done. In this process, we got that v to the other side. The dv's on this side. So we're going to keep the dv on this side, but then take this and divide it over here. They just flip it. That's fine. And then here's probably, I've never done this before, but you have to figure out, or let's see what they do. They actually have to get the denominator. The denominator can be factored. So this is square root 1 plus v squared. This is 1 plus v squared. I guess it can be factored. I have no idea. But yeah, they're going to take this and factor it to this. I guess that's just some math manipulation that you have to know. That sucks. That's why I'm doing this video. It's like, this isn't helping you understand the final solution anyway. You know what I mean? Like this type of math. But it's cool. I guess it's cool if you know how to do it and you're just like, hell yeah. I know to factor. I can't see it right now. This sucks. Well, maybe I see that's really tough for me to see. I don't see it. Cool. But yeah, I'll solve this one on my day off. Hell yeah. Alright, so they factored it. Now what? You're going to have to integrate both sides. To do the integration process, you will probably... Well, let's see. Now integrate both sides. For the left side, yeah, you have to use u substitution. So we're letting u equal this. And then du is going to be the derivative of this. So this is going to go away. So du is just the derivative of this. How do we do the derivative of kind of any function? Is Yeah, so if we're taking the derivative of this, du dv, you would use u substitution again. So the derivative of this with respect to v, du dv, is going to be, well, let's come up with a, let's just say this is u substitution. So u is going to be 1 plus v squared. So then I'm going to have u to the 1/2, and I'm going to take the derivative with respect to, oh, this is where you use that rule where d, and I'm going to call this du prime. So du prime is, so what I want to find is du prime dv. So the derivative of this with respect to v, I'm going to say that's du prime du, and then du dv. So this is the u substitution part, right? Maybe not. Oh, I'm getting tired. No, that's exactly how, it should be. But yeah, so you're going to have the derivative, this u is now going to be 1 minus u to the 1/2. And we're going to take that with respect to u. This doesn't have a u in it. This I'm going to go negative 1/2. Yeah, fair enough. I'm going to go negative 1/2 u to the negative 1/2. Cool. And then we have to so that's that part, and then we have to take du dv. And so our u was this, and we need to take du dv, which is just 2v. And that's what we're going to multiply right there, 2v. And so now we have the derivative of this with respect to, so this, and then substituting back in, 1 plus v squared to the, to the negative 1/2. This is now du. So du is equal to all, oh, and then this is 2v, I'm sorry. No, du dv is 2v. Yeah, we're good on that. Right there. And then this is du, this is du dv. So du dv, the derivative of this with respect to v is that. And that means du is equal to that we just solved for, dv. Holy hell. It's good for me to at least talk through this once and see where I come up with the hiccups. But yeah, we did not explain that well. But anyway, I just need to move on. And what were we even doing there? Now integrate both sides. For the left side, you're going to let this equal u. And then du is equal to all that. And then we actually see that. So this right here is right there. And you're like, holy hell, sweet. And look at that. That's right there. So this is just going to be du. We're going to have a negative. It's going to be negative du. So now we're going to have negative du divided by u. And then, sweet. So that's what we have on that left side. Negative du divided by u. We're going to take the integral of it. The negative is like a negative 1. It can be a constant pulled out. And this is just going to be, the integration of this is natural log. So it's negative natural log plus a constant. And then substitute u back in. That's where they're substituting the u back in. So they still left, probably missed a step there. Anyway, so then, yeah, that's the solution to that left side. The right-hand side is just integration dxx, which goes to natural log, I guess, plus another constant. This is the left-hand side. This is the right-hand side. The integration of the left-hand side, the integration of the right-hand side have separate constants, but then when you put them in the same equation, you can get the constants to one side and just call it, C3, or they call it just C. Because there's natural logs on both sides, you can take e, you can raise both sides to the power e to the power e to both sides, and then it basically kind of gets rid of the natural log. So let's look at this. So this, if this didn't have a negative here, this would just be on top. It would just be that on top. Because the negative here, it makes it 1 divided by. And so, so that's what we have there. Alright, and then this side just becomes this absolute value of x. I don't know why you get to just... Oh, is it the fact that this isn't... Well... this sucks. Is it the fact that this isn't part of the natural log? I have to figure that out. Is that why? That this c actually just goes outside? Because this is also e to the c? Because you would have e to the x and then you would have e to the c, right? I'm not quite sure about that. But anyway, even if it was e to a constant, you have a constant to a constant. It's just another constant, and it's being multiplied. So that's where that goes. So that's a good enough explanation. So a is this new term, and it's going to be our new constant. And that's what we're going to follow through. And this says, since x and y are real, this v, y divided by x is real. It means this term is always greater than or equal to 1. What's a real number? Oh, well this is going to be squared anyway, so you're going to have 1 plus something, and then you're going to have 1 minus, this is 1 plus a positive number. This is always going to be bigger, and so you're going to have 1 minus a bigger number. This is always going to be negative, but it's the absolute value. And then so, yeah, so this is always greater than or equal to 1. And then so, yep. And this is always going to be positive. So they know it's always going to be positive, so they're going to get rid of the absolute value sign, because if you get rid of the absolute value sign, you can write it in 2 different ways. You're just going to do the positive one. And so they rewrite it as this. So they just switch the order, and then that always makes this positive, because this is always positive. Because what did we say? It's always going to be positive. You know what I mean? And then so this is bigger, this minus 1 is positive now. So that's what they did there in that step. That sucked. Factor in, or put back, substitute back the y divided by x for your v. And so now what? Well, I don't know. Oh. Well. And then so you're going to have y squared divided by x squared. To get these two the same, you're going to have x squared divided by x squared. So now you're going to have x squared plus y squared divided by your x squared. That's underneath the square root, so we can pop out just an x. That's what they did there. And so, and then what else are we doing? This comes to the top, and then that factors out. And so, and then we can get the a, this over here with the a, and this is just 1 because it factors out. You know, you can bring the others to the other side. Anyway, and then so, what else are we doing? So that's the same term right there. Oh, they're going to take this a to the other side. It's going to be 1 divided by a. So now they're going to say 1 divided by a is b. They really don't tell you that. Cool. But now the whole thing is we have x's and y's, and we only have one y. That was the wild thing. Even just right here is just like, what are we doing? Well, you only have one y. So go solve for y. Cool. Now we can solve for y. We still don't know what the constant is, but that's where we're going to use our initial conditions. We change the constant b, you know, from there, because b is 1 divided by a. But anyway, let's solve for y. So I'm going to take this, square both sides. So this becomes x squared plus b squared plus 2xb. And so that's what we have right there on that side. This side is still just x squared plus y squared. I'm going to cancel out the 2x squareds. This is what we get boiled down to. Y squared is equal to this. And I'm going to apply the initial conditions. So the initial condition said when x is 5, y is the square root of 56. So y is 56. And so that's what we have right there. So we have 56 right there, 10 right there, and then we still don't know what the b squareds is. So you're going to treat it like a quadratic. Just get everything to one side. Your a term is 1, your b term is 10, your c term is negative 56. Or just factor it into these two terms, and then we're going to see what's possible. So when b is negative 14, that's going to be a solution. That means that, let's go back to if b is negative 14, our initial condition says this is 5 and this is 56. So when b is negative 14, and this is the equation that they sub it back into it. But yeah, if this is 5, you're going to have 5 minus 14 is, so they're taking it all the way back to this equation. That's fine. You can use any one, but maybe it makes more sense to use that one. So 5 minus 14, that negative 14, is going to be a negative. This can't be a negative number. So that doesn't work. So this, b is equal to 4. 5 plus 4 is 9. And then let's see if that works. 5 plus 4 is 9. And all right, hell yeah. And then so if the initial condition says this is 5 plus 4, that was one of the solutions, is 9. And then we would have 5 squared. Yeah, 5 squared is 25. Plus this is square root 56 squared, which is 56. And then so you have that, which is 1, 5, 6, 7, 8. You have 81. Square root 81 is 9. So 9 is equal to 9. That checks. And so that's what they show right here. And so, sweet. So b is equal to 4 is the correct value. What the hell does that even mean? Cool. Now we have this equation that's y squared is equal to 2bx plus b squared. So b is 4. And so we have 16 here. We have 8x here. So we have 8x plus 16. Y squared is equal to 8x. Y squared is equal to 8x plus 16. And so we can say that y is the square root of 8x plus 16. And that's why, back to our graphs, that's why we got that graph that looks like this. Dy dx is going to be, if we do u substitution, this is going to be u is equal to, u is equal to 8x plus 16, du dx is equal to 8. And then so I'm going to say this is y is equal to u to the 1/2, and I'm going to take dy dx, there isn't an x here, is equal to dy du, dx. And so dy du is going to be 1/2 u to the negative 1/2. Du dx is going to be 8. And so we're going to have 4 u to the negative 1/2, which is 4 divided by the square root of 8x plus 16. And so that's what we have. As x goes to infinity, dy dx, because this top is a constant, we talked about that, then just peters out. So that is our equation for dy dx. This goes to 0 as x goes to infinity, where and the slope approaches 0, but it doesn't get to 0. The slope is still positive, always positive. And then so even our graph that goes like this, even when we're way out near infinity, we're still having a little positive slope, so we're still going up. You know what I mean? And so even though we're going up shallower, there's no asymptote there. It still can go to positive infinity that way. It's just doing so very, very slowly. So this is one of those, you know what I mean? Hey, something is growing, but now it's growing progressively slower and basically stop growing. Still theoretically get to infinity, but that is the definite. That's why this goes to infinity, this goes to 0, approaches 0. Where the y, as this goes to infinity, the y actually goes to infinity as well. So Alright, hell yeah. Alright, that was differential equations. And I haven't done differential, you know, like put solid effort into like a question like that for a differential equation. I would just do easy ones maybe. But yeah, I think we did it. This video was challenging for me, but it's good. You know, I'm glad I'm actually saying words and seeing what makes sense, where my hiccups are. That was brutal to get through that Google, you know, about use substitution. When are you using chain rule? Did I confuse chain rule with product rule? Yeah, I confused chain rule with product rule. So sorry about that. I'll have to go review that. Alright, hell yeah, we did our first differential equation. That was pretty difficult. Thanks for joining me. Hell yeah.